Uh, my name is Mohammad Khosravi. I'm a postdoctoral researcher at UC Davis, and we're honored to have Professor Boulanger for the webinar today. As you may all know, Professor Boulanger is the director of the Center for Geotechnical Modeling at UC Davis. He received his PhD from Berkeley and his undergrad from University of British Columbia. And his research mainly focused on liquefaction and its remediation, seismic response of dams and the structures. And for today, he's gonna talk about the remediation of liquefaction effect for embankment dam using soil cement walls. He has received many awards. I'm not gonna list them here because of the lack of time, but the most recent one was his election to the National Academy of Engineering. So Ross, you're welcome to start.
Thanks, Mohammed. Yeah, well, welcome everyone. Always a challenge giving a webinar because I can't see your faces. So hopefully, as I go along, Mohammed will wave at me once in a while and tell me if nothing made sense or if he's getting a lot of chat remarks or questions. And hopefully we can get to them all at the end. Also, just to start, that this is one of the NCO webinar series looking at research to practice, and particularly through the NHERI network. And so I'm going to go through this one example research project to illustrate how the centrifuge facilities at UC Davis, one of the facilities in the NHERI network, has been used to kind of bridge issues of research through practice and support industry. And as I go along, I'll also try to point at some of the resources available to learn more about our facility in terms of its capabilities, arrangements for users to get access to it, our recharge rates and things like that. So I'll try to touch on some of those things a little bit later. Okay, so my talk, the project we're going to look at is the use of soil cement walls to remediate liquefaction effects, and we're focused on embankments. And the motivation for this comes from a number of projects in the US. I've listed 5 of them here where soil cement walls have been used to treat embankment dams for problems involving liquefaction, usually in the foundation of the dams. And these 5 projects all look surprisingly similar to the one in the bottom figure, Clemson Diversion Dam. And the key here is these older dams were often built on a layer of materials that's later determined to be liquefiable. So often built in the 1960s or so. Later, we find that we've got to treat this thing for liquefaction effects. And the objective is not to prevent liquefaction throughout the foundation layer, but rather to minimize or mitigate the amount of deformation at the dam crest. For that reason, a common strategy is to treat a portion of the foundation with these soil cement walls or grids, and provide maybe a berm to support it and confine it. And this helps mitigate any deformations at the dam crest and reduce the potential for breach of the reservoir. So that's the idea. Of these, 4 of these projects are in California. They are projects that I've been involved in a couple, our colleagues and friends on the other projects, and we've all had some common concerns that have kept coming up. And these concerns regard to how we are analyzing them. So a common analysis approach on all of these has been the use of a 2-dimensional model, even though it's going to be really a 3-dimensional problem, and using a composite or area-weighted set of properties for the treatment zone, and then how we model them. And we had no experimental data to really be sure that these models were working well. So the questions that have routinely come up on these projects, amongst many questions, have included these 2. First one is, will the soil cement walls, or these grids, will they be effective in reducing deformations if the walls crack extensively during strong shaking? And so how does that cracking and loss of strength affect their performance? And the second one is, how well do these 2-dimensional analysis models adequately predict the behavior or benefits of these soil cement walls or grids? So that was the reoccurring question on these projects. So our approach in looking at it's pretty straightforward. Show you the results of a dynamic centrifuge model test where we use soil cement walls, and these are designed specifically not shear or crack extensively in one shaking event. Even though we'll liquefy the soils, we won't damage the wall badly. Then we're going to shake it again, and we are going to shear those walls off quite extensively. And we want to see how the walls perform in that case. And given that data, we're going to do a two-dimensional nonlinear dynamic analysis. We're going to follow what are essentially the same practices that are commonly applied in these projects that I was just referring to. We use composite properties in the treatment zone and the same kind of procedures and protocols that have been applied to those projects. We want to see, in hindsight, can we validate the method that has been used to design those remediation projects. For the outline, what I'll do is I'll start with just a quick overview of some of those 5 remediation projects, just to show you the geometry of them, some general features, just a couple comments on soil cement strengths that are relevant to the design of the centrifuge test and how we're going to model it. Spend more time going through the dynamic centrifuge model test itself, the configuration, and some of the observations. And then we'll get to the nonlinear dynamic analyses. And here I'll have to walk through first the model development and how we calibrate, select the parameters for the analyses. And then we'll show the comparison of the numerical results with the experimental data, see how well we do, and then we'll have a few points of discussion and we'll wrap this thing up. That's the plan. First thing is you can't do this kind of work without a team. And so this particular set of experiments analyses that I'll be describing were performed with Mohammad, who just introduced me, his brother Ali Khosravi, and then Dan Wilson, who is our associate director here at the CGM. So that's our team, and I'm going to walk through the rest of this now. Okay, so first, go over those remediation examples to give you just a sense of the scale for these different projects. We already went through the Clemson Diversion Dam. I would point out it was about a 24-meter high embankment. And the soil cement grids were targeting a strength, unconfined compressive strength of about 3 MPa. Sunset Basin Dam, it's about 23 meters high. And again, you see very much similar strategy where you have treatment in the foundation, in this case, in 3 sets, distinct sets of treatment zones. Target strength here was about 2 MPa, which I'm pointing out this because that's going to go to the strengths that we used in our centrifuge model. And this is just a plan view of Sunset North Basin to show that the soil cement walls in this case are arranged in grids. These grids have these longitudinal walls to help support the walls against any transverse loading across the long axis of the walls. But they often have gaps, and these gaps or windows are there so that the soil cement improvements don't back up the groundwater flow. So you have to let the seepage continue. And so the amount and size of those windows is one of your design considerations. And then this is Paris Dam, a very similar configuration with 3 treatment zones and a berm on the downstream side, about a 39-meter high embankment, about 3 MPa was the target strength. And then Chabor Dam, similar idea. This is about a 30-meter high dam, again targeting out here, about an MPa of strength. And then this is San Pablo Dam, 44-meter high. So again, I kind of get the sense of these dams are 20, 40 meters high. Treatment zones all at the toe, very similar strategies. Just a couple comments on how these soil cement walls are often built. 2 common ways. One is just to use a long reach excavator. In this particular case, the excavator reached down to bedrock at about 20 meters depth. Rock was the Franciscan Formation. It's not particularly hard rock, but there were still problems getting keyed into the rock. So the soil cement walls are properly locked in place into the bedrock. Soil cement mixing, deep soil mixing, instead using overlapping augers, has a little more effective because the teeth can grind or key into the bedrock. And this is just a photo of a soil cement deep mixing operation in the test section. In particular, this was at San Pablo Dam. where these will all be just overlapping panels, and they were able to key in the bedrock, and this is the method that was chosen for production on this particular project. It kind of gives an idea of how these things are built, how to key them into bedrock, etc. Okay, a couple quick comments on soil strengths, which relate to, again, design of the centrifuge experiments. If you look at design strengths for deep mixed soil cement in situ, a good reference is the FHWA manual from 2013. Covers an awful lot more detail than we're going to talk about here. What I mainly wanted to point out is that commonly take the shear strength of the soil cement as being a half the unconfined compressive strength with some factors applied to it. One of those factors is to relate the ratio of your confined large strain shear strength. So in the field at depth, we got some confinement on it. We want to know what kind of strength we'd have when we get a significant amount of strain in it. So that confined large strain strength compared to the unconfined compressive strength. And that ratio is typically something like 0.65 to 0.9, and a value of about 0.8 is common. There's also curing time factors and spatial variability factors. And in our case, because the models are being constructed in the centrifuge, we do our strength test at the time the centrifuge test is performed, so we're actually getting the strength at the right curing time. And our models are quite uniform, so we don't have the spatial variability issues. And we're really going to be testing how well we can model the behavior of these soil cement walls at larger strains and when they start to crack. That's really what we're keying in on. A couple more things about that issue of what strength to use. It's kind of illustrated in these tests by Tatsuoka and Kobayashi. And here they're showing traxial test results, ICU traxial test results on a stabilized Tokyo Bay clay. These two lower plots here are what you get if you have unconfined tests. Without confinement, after you reach peak strength, they're quite brittle, as you'd expect for an unconfined specimen. If you provide even a modest level of confinement, not just a few kPa, a few tens of kPa, you get quite a good ductile response. And so you can see maybe you're hitting peaks up here, and then by the time you're out at 8% strain, you may have only degraded 10 or 20%. So they're quite ductile with a little bit of confinement, provided they're saturated and undrained. Now, in other soils, you do get a little bit more degradation. And George Fields has been doing some work on this, and he's described some tests where he gets a little bit greater rate of strain softening for a soil cement treated loamy soil. So we want to be a little bit cautious in how we do this. For our purposes, what we're going to do is we're going to use 80% of the peak strength. And the logic, it builds on what I just described, but a little more, or one more step to just think about. And that is, if during earthquake shaking we go up and we have a peak resistance, and shaking keeps imposing more demand on the system, and at some point the strength degrades, and if it degrades to say 60% of the peak by the end of shaking, then in terms of trying to predict resistance to deformation, we had 100% early in shaking, 60% later in shaking, 80% is our choice as kind of representative of what you might have on ASCE. That was part of our argument. We used on a number of things. We use this 80%. Okay, so that's that background. Now we get to the centrifuge model testing. The tests that I'm going to describe is on the 9 radius centrifuge here at Davis. Again, this is part of the National Shared Use facility under the Natural Hazards and Engineering Research Infrastructure Network. And so again, 9 meter radius to the end, the payload on the end of the container or the arm is about 10,000 pounds. Models with the soil in it are about 4,000 pounds, and the container is about 2 meters long. Now, anyone's interested in more details about the centrifuge? I think somebody out there is typing while they've got their microphone not muted. So you might want to mute your microphone if you're typing. Okay, thanks. So that's our centrifuge. We also have a 1 meter radius one, but the test I'm showing you comes on this one. Container is about 2 meters long in life. We're going to be doing this test at 65 Gs, and then I'm going to present everything in prototype units so that it's a little bit more relatable to field conditions. What that does is it turns the embankment into about 28 meters high, which is very comparable to those projects I was describing, over about a 9 meter thick layer of loose Ottawa sand. The sand is treated near the toe with soil cement panels. The soil cement panels are keyed into our bedrock. Our bedrock in this case is a concrete base in which the soil cement walls are slotted and then anchored. And the bottom part, the loose Ottawa sand, is saturated with a methylcellulose water mixture, which has a permeability of about 15 times that of water. That's the configuration of our embankment dam. And we chose to build the embankment taller on one side. This allows us to, we know the mechanism of deformation in this direction, and our focus is on how this soil cement wall is going to perform with this bias displacement of the embankment. That's the plan. In kind of a three-dimensional view, you can see that the treatment zone is actually a set of parallel walls. And these longitudinal walls, when we shape the model, it'll be in this longitudinal direction. We don't have cross or transverse walls to turn them into grids. That's just for convenience in building the model. In reality, you usually have a bit of that. And the whole test was again in a flexible shear beam container. This is a photo of the model on the arm of the centrifuge. Just looking down from the top, these are racks to mount displacement transducers and cameras, et cetera, on. The blue is just colored sand so that we can see deformations during shaking with the high-speed cameras. And then this is the crest. It's going to move towards the right and deform out to the toe. Now the model is going to be shaken 3 times. All 3 motions are scaled versions of a record from Port Island in the 95 Kobe earthquake. Take that record and we're going to scale it to 0.05 G. This is a very low level of shaking. It doesn't produce excess pore pressure, and it just allows us to test the elastic response of the system and make sure all the sensors are pointing in the right direction and working correctly. I won't be showing you that one. The second motion is scaled to 0.26 G at the base, and this will cause liquefaction in the loose layer, but it won't cause a lot of damage to the walls. Get a little cracking, but not extensive damage. And the third shake is have a peak base acceleration of about 0.5 G. And in this case, we will shear those walls off. And so we'll have those 2 cases that we'll be analyzing in more detail. The soil cement walls, they were mixed and formed and cured in molds outside the centrifuge. They are in prototype 1.4 meter thick walls, spaced 5.8 meters apart. That gives us an area ratio of 24%. Unconfined compressive strength at the time of testing was 2 MPa, so right in the range of those remediation projects I described. And then we had crack detectors embedded in the walls that allow us to determine when damage happens during shaking. These are photos of the walls after the test is completed, and we've excavated all the sand to be able to look at the walls. The embankment will have been moving from the right towards the left, so this is the toe. And as the embankment was moving, you can see the complex cracking patterns that have developed in the walls. Most of this happened in the large shaking event. You can see offsets where the upper part of the soil cement walls have offset relative to the base. That offset is about 0.8 meters. You see these wires going into the walls. Those connect with these conductivity crack sensors. And now, in the first shake, we got some cracks at the front of the walls, but not all the way along the walls. In the second big event, that's when we sheared a whole length of these walls and produced these offsets. Now we can also look at how things formed by examining these excavated models. And in these photos, there's one from before testing during construction of the model, and then one after the test and we're dissecting. The toe of the berm is at the bottom, so the sand was moving from top to bottom. This blue is a very weak paper that's embedded in the model at a couple elevations. When it gets wet, it's just very weak. And you can see that it was originally placed against the soil cement walls, and it has pushed or it kind of intruded in the gap between the walls, and at the bottom pulled away from the walls. What this shows is that in reality, we got a little bit of sand extruding through the space between these longitudinal soil cement walls. Part of that is probably greater than might happen in the field if we had longitudinal grid boxes, but it goes to the fact that these are three-dimensional systems. That kind of mechanism we're not going to catch. I should point out that sensors, we know that the sand in between the walls also liquefies during shaking. So when this is all liquefied, it's got that ability to ratchet and move relative to the soil cement walls. Okay, so that's a overview of the centrifuge model. I'm going to talk about how we're going to do our analyses. The analyses are performed using Itasca's FLAC 8.0. It's a two-dimensional coupled simulation. In this model, the foundation, the loose Ottawa sand, and the embankment. The embankment, I think I forgot to mention, is a dense, dry Monterey sand. And both of those being sands were modeled using the PM4 sand constitutive model, the version 3. Describe that in a second. That's probably the dominant model of concern here. The second one is for the soil cement. We are going to use a more Coulomb model with area weighted properties. This is not a very sophisticated model for soil cement and cracking, but it is the model that is used on those projects that I described. And so we wanted to replicate practice to see how that kind of modeling worked. The container is modeled as elastic. We know the properties of the the aluminum rings and the rubber spacers in the flexible shear beam container. So those are very well known and very predictable. And then the bedrock layer is this concrete base, and it's modeled as elastic as well. So that's the basic model. The constitutive model for the loose Ottawa sand and the dense Monterey embankment, I mentioned was PM4 sand. This is a version 3 of the model that was developed by myself with Katerina Ziotopoulou. It's a critical state and stress ratio based bounding surface plasticity model. It's developed specifically to approximate those types of things important to earthquake engineering practice. The model has quite a number of parameters. The way we put this together and developed it was we prepared a generalized calibration to make this easier for others to use. And with that generalized calibration, most users are going to work with 3 primary parameters. You're going to estimate the relative density, DR. You're going to estimate a shear modulus number, which you anchor to your shear wave velocity data, so you get the small strain modulus right. The density comes from, say, your blow counts or CPT, cone penetration test data. And the last one is a contraction rate parameter that's used to calibrate the model for cyclic strength that you're going to estimate by whatever means you find appropriate. And all the other parameters have hardwired default values that you can override or not. And we're going to use all the default values for these simulations. Again, see how that would have worked in practice. If you're interested in the model, the dynamic link library, the manual, and all the example files for calibrating it are available at this link. You can get it off my homepage or Katerina's homepage. If you have a chance, let us know how it works for you. Okay, so this is a calibration process. In this particular case, we do have quite a bit of experimental data for Ottawa sand. So we do have Emax and Emin values. So we did use those instead of the default values. Then when it comes to cyclic strengths, we use the simple shear test data by Ana Maria Parabastidas, which is shown here. These are tests, different confining stresses for loose sand and a little bit denser sand. And using this lower set of data, 15 cycles right about here, you would have triggered liquefaction with a cyclic stress ratio of about 0.09. So for our first set of calibrations, We know our sand was placed at a relative density of about 42%. We know the shear wave velocity for this material and its small strain modulus, so that sets G naught. And HP0 is the calibration constant that you adjust until you get a cyclic strength that you want for the overburden stress that is applicable to your model. And in our case, that is about 400 kPa under this embankment. So that's the first calibration. Now, the second thing is that we're going to shake this model. We liquefy it in that second strong event, and the model gets a little denser. Now, Anna Maria had done some additional testing, and this test is showing cyclic strengths versus void ratio, where she'd start with specimens at loose conditions, cycle them, liquefy them, let them reconsolidate, and then retest them. And the cyclic strength will increase as those specimens go through liquefaction events. And so based on these data, we estimated that for the third strong shaking event, we know we're a little bit denser because we've settled. We'll be a little bit stiffer because of that. And our cyclic strength would be about 20% greater, about 0.12. We'll test these numbers in sensitivity studies, but those are going to be the baseline calibrations that we used for the analyses. Just to illustrate what the constitutive model response looks like, this is showing a stress strain response in the stress path that the model would simulate for that second calibration, 45% relative density. You can see the model picks up the cyclic mobility and accumulation of strain during cyclic loading, and recreates the path that you'd expect with this butterfly behavior down here, getting temporarily zero effective stress or 100% pore pressure at that point there. That's what the model looks like. We're also interested in testing how the model behaves under a regular loading path. I'll throw these in as just examples. The first thing we're going to do is in this top graph, you see is a stress strain response with uniform cyclic loading, but with a static bias on it. The static bias is to approximate the effect we have a slope, so we always have a driving stress in one direction. When you do that, the stress strain response is going to accumulate strains in the direction of the driving stress. That's pretty much what we expect, and you like to see how your model behaves for that kind of loading condition. In this case, the static shear stress ratio is about 0.06. We repeated that where we run the same loading up until we trigger liquefaction, and then we drop the cyclic stress ratio by about 2/3. And then you see that it accumulates strain at the lower level, but at less strain per cycle, which you would expect for a lower loading level. And the reason we're doing this is just to see how the model behaves reasonably well on their loading paths, similar to what we're going to get in the full boundary value problem. And if I didn't mention it, I should have pointed out that these simulations are all in single, simple shear elements to simulate how the constitutive response performs at the element level. And it's just part of the calibration process. That's some examples of the behavior. Okay, so now to go into building the model, some interesting things. We're going to need hydraulic conductivity. So for the Ottawa sand, we have experimental data for its hydraulic conductivity. In this particular case, the lab tests are with water. When we do it in the centrifuge, we go up to 65 Gs. We don't scale diffusion the same as dynamics. So this means that we will be modeling something 65 times more permeable. Then we have a higher viscosity pore fluid. We used 1/15. Part of that is you go too high on the viscosity, it can be hard to saturate the models. You put the two together and that gives us our net hydraulic conductivity to use in the numerical analyses. The second part is we need data for the Monterey sand. Monterey sand is more permeable. So in the portion of this Monterey sand that's just above the water table, it's about 10 times more permeable than the Ottawa sand. And then as you go a little bit above it, you get into the little bit of capillarity zone, so you're partially saturated. And just using empirical soil water characteristic curves, permeability drops a bit, quite a bit, when you're partially saturated. And so we include that as well. And I'm going to come back to that as a sensitivity study later to illustrate some things that are interesting about that. Okay, so now that's the constitutive model for the sand. That's the permeabilities. Now we need the soil cement. In the soil cement here, what we have is the Mort-Coulomb model that we're going to use. B equals 0. And now we just need the shear strength. We're going to use 80% of the peak strength that we get from our unconfined compressive tests on our soil cement specimens. And that gives us our shear strength of the panel is 0.8 times half of our unconfined compressive strength. Now we're going to we have to have the composite strength. Now in the Ottawa sand that's below the water table, we're going to assume that the sand in between the panels, which we know liquefies from the pore pressure transducers, that is essentially so much softer than the panels that it's going to offer no resistance. And so the zero resistance from the liquefied sand, then the strength of the composite zone is the area ratio, 24% times the SU of the panels, and that's how we get the composite strength, just like we do in practice. When you look up into the dense Monterey embankment, those soil cement panels extend up in that zone, and that soil doesn't liquefy. It's denser, it drains really rapidly, so we know we don't have pore pressures, excess pore pressures in there. Now we're going to use drain strengths, therefore, for the dense Monterey sand between the panels. And then we're going to use area weighting, not just of the shear strength of the panels, but also area weighting of the frictional strength of the dense Monterey sand. It just makes it a little bit stronger up there at the top. That's pretty much all the details of the numerical model was done. Now we get to look at some results. These are going to be for that second strong shaking event, peak base acceleration of about 0.26 Gs. And again, this will produce a little bit of cracking in the fronts of the soil cement walls, but it was not extensive and it didn't extend their whole length. So in these next set of diagrams, I'm going to be showing some time series. On all of these, I'm going to show in the upper right corner is an inset of the centrifuge model, and it's going to show the sensor locations that we're plotting. So these red triangles are locations of accelerometers, and those accelerometers are these 4 acceleration time series over here on the left. The bottom is the base, and this moves up through the embankment to the crest up here on the upper left. The next 3 over here in the mid-face of the embankment, and then the 3 on the right are these ones on the soil cement wall, the berm, and then out in the free field. If you look at these accelerations, generally across the model, the simulation in red is doing a pretty decent job of approximating the measured responses. Look a little closely, you can see that the simulation in red has a few strong acceleration peaks in areas that have liquefied. And these strong acceleration peaks are associated with that cyclic mobility behavior. So when the sand is gone to zero effective stress and then is starting to strain harden on one of those cyclic mobility steps, you're going to get essentially a shock wave or a stiffening of the material, and you get these high acceleration spikes. And in this case, they are higher in the numerical analysis than they are in the actual experimental data. That happens. I'm going to show you the opposite on the next one. These are the pore pressure transducers. The 4 on the left are underneath the embankment where the overburden is stress. Stress is high, and because those are high, these excess pore pressures rise to very high values. Generally, it triggers very early in shaking, and the model tracks them and the dissipation reasonably well. These 2 on the right are out at the toe where the overburden stress is not so high. They also trigger liquefaction. Just the magnitude of the pore pressure is not as high because the overburden stress is not as high. So doing reasonably well there as well. These are the displacements. The upper one is the vertical settlement at the crest, and the lower plot is the horizontal displacement of the berm over the treatment zone. And you can see that we're capturing both the magnitude and amplitude of oscillation in the berm displacements pretty well. And we got the crest settlement also pretty well, just maybe a few percent overestimating. So that worked really well. This figure is showing the contours of shear strains in the numerical simulation. White box is the outline of where the soil cement grids are. Remember, the numerical model is a uniform 2D model, so it's not getting the 3D aspect. And what it is predicting is that through this composite treatment zone, you'd be getting strains on the order of maybe 8 or 10%, which is pretty significant. And yet we were not getting cracking in the soil cement walls. And part of that is this is a composite response. In reality, the strains in the soil cement were probably smaller, and the sand in between the walls is going to get larger. It extrudes between the two. And so there's some compensating effects there. And then strains back in the liquefied sand to under the embankment are maybe 10, 12%. This is the stress strain response for a point underneath the embankment from the boundary value problem simulation. And what you see is early in shaking, you trigger high pore pressures, the model gets softer, the dynamic loads dropped off because due to liquefaction in this particular system, the demands on the soil are dropping. And this looks a lot like the single element simulation I showed you earlier. And that was the motivation to just be able to see under single element and under the boundary value problem that the two behaviors are all making sense. And you see we're getting maybe something on the order of 6 to 8% in this area. Okay, so that was pretty reasonable agreement, and it was a case where the soil cement walls were not badly damaged. So now we wanted to test it under a more severe loading, and now we've essentially doubled the base acceleration. These are the accelerations, same format as shown before. So when you look at these, in this particular case, you see the simulations in red are now not getting the highest peak acceleration spikes down in the liquefied layer right across there. But in fact, the black lines here are the measured data, and the measurements are showing even stronger peak accelerations associated with that cyclic mobility response of the liquefying sand. And getting those high acceleration spikes is pretty tricky because it's kind of like a shock wave phenomena. It's very sensitive to the rate at which a soil strain hardens in that cyclic mobility response. And so this just goes to the fact that that cyclic mobility behavior and these acceleration spikes, we see it in lots of different experiments. We've seen it in the field. Numerical simulations can recreate it, but actually matching it on a one-to-one basis is pretty tricky. But those are really high accelerations and high frequency accelerations, and so they don't really cause a problem in terms of predicting deformations. When you look at the longer period components, the responses across the different parts of the embankment from the crest out to the berm are still looking pretty reasonable. These are the excess pore water pressures, same format as before. This is very strong shaking, as I mentioned, 0.54 G at the base. And you can see these measured pore pressures in black. You get these very strong dips in pore water pressure. Those are associated with the strain hardening and those high frequency acceleration spikes. And the simulation is by and large getting most of that response. These are the crest settlements. At the top, we're probably overestimating crest settlements by maybe 50% or so, but we're getting the berm displacement still pretty well. So put those together, this is the simulated shear strains in the model. That's where the soil cement wall is. Now we're predicting shear strains in the composite zone that are more like 30%. Even at that level, even if the soil cement wall gets less and the sand between the walls gets more, that is enough strain badly damage the soil cement walls, which is in fact what you saw when we looked at the excavated walls. And we also have those crack sensors, and the crack sensors show us that all the way along the length of all the walls, we shear those things off pretty quickly. This is the stress strain response for that element underneath the crest. In the liquefying Ottawa sand layer. Same kind of idea, triggers early and then it accumulates strains. Now we're getting out to about 16, 18% strain, depending on where you are. And it looks very much like the single element simulation. So all seems to be working reasonably well. Okay, so we have baseline analysis model, calibrated the way we described. and results were looking pretty reasonable. What you really want to be able to do is just look at sensitivity and understand what are the parameters controlling this behavior. I can't go through all the different things we examined, but I'm going to show you some of the key ones. So the first thing I want to do is walk through how sensitive the simulations are to the choice of the soil cement strength. And so the left figure is going to be the crest settlement of the embankment, plotted versus the percent of the peak shear strength assigned to the soil cement. Right? So we know the unconfined compressive strength is 2 MPa. We use half of that as our shear strength, so that's 1 MPa. And this is our baseline model. We used 80% of that. And we got that point. We predicted about 0.3 meters of crest settlement. Figure on the right is the same format, but it's horizontal displacement of the berm. So if we come over here and look at the crest settlement, the measured settlement was about 0.3 meters. So we got that pretty well, both at the crest and at the berm. If we change the soil cement strength, and instead of using 80%, we're a little more conservative and we use 60%, we get not much more displacement. And if we increase the soil cement strength by as much as 150%, which is enough to essentially make them elastic for this 0.26G motion, then you get a little bit less. But it's really not that sensitive to that range of shear strengths in the soil cement. If we go much lower, this is going to pick up a lot. If we go much higher, it doesn't change. So in this range, really wasn't that sensitive. In terms of berm displacements, it was more sensitive. And the reason it's more sensitive at the berm is because we're measuring displacements at a point right over top of the soil cement. And so if we make it a little weaker, we get significantly more movement locally, even though it doesn't manifest as a proportional increase up at the crest of the embankment. So a little more sensitive down here. And it turns out 80% was a very fortuitous pick. Again, that number is very much like what we use in practice. So just kind of was a good moment feeling that what we've been doing was reasonable. This is the 0.54G event. Over here, the measured was about 50% larger than, the simulation was about 50% more than what was measured, but the berm displacement was pretty good. Same kind of story. The crest settlement was not so sensitive to the strength that we assigned to the soil cement, whereas the berm displacement was considerably more so. So that gives us some idea of sensitivity to that particular strength parameter in representing this treatment zone as a composite uniform material. And generally, we were overestimating crest settlements in the Kobe event, no matter what we did. Why were we overestimating crest settlements? Well, what we believe we see when we look at the numerical simulations is we get this wedge moves to the left, and this block of the embankment is more or less moving horizontally and has a bit of a rotational component to it, and that produces more crest settlement than we're getting in the actual experiment. So it just goes to some of the approximations in the model. So we tried to look, could we reduce that? And the answer is, yeah, you could reasonably to a degree. And so we looked at if you strengthen the embankment, either by making it denser, some uncertainty in how dense it was actually placed, or in the parameters describing the dilation angle that you get out of the model. If we do that for either the embankment or the loose sand, we can reduce crest settlements and get it to agree better with the measurements. But the reality is, if you do that, you're going to underpredict the deformations down at the berm and in other locations. So there was no one set of reasonable variations that was going to get both of these behaviors bang on. So there really was no one issue that was going on. It's just a limitation in the modeling. Okay, some other things that I think are interesting from the parameter studies. One is the loading history. So the simulations I just showed you, we start with the same baseline numerical model and we apply it for the two different events. But in reality, they're applied to the model sequentially. So what we do is we take for the Kobe 0.54G event, we first ran it through the 0.26G event, and we kept that model in its deformed shape and its new relative densities because it will have developed shear zones that have dilated or contracted, and so it has a different distribution of relative densities. And then if we do that and shake it with the 0.54 G event, we get about 30% more crest settlement than we get if we did. That makes sense because the 0.26 G event does cause some prior dilation in certain zones, essentially weakens the material and makes it more susceptible to deformation in the stronger event. So that sequence of loading does play a role. And then hydraulic conductivities. This was an interesting example of it's not easy to tell what's conservative sometimes. So one sensitivity study is we did a no flow analysis case. This is common in practice sometimes. You don't have to estimate permeabilities if you just say there's no flow. And so it's pretty common to do that. And if you say you have no flow, we actually get less crest settlement. It was about 45% less for both Kobe events. Normally you think that if you turn off flow, turn off drainage, you should get more displacement. In this case, you don't. And the reason is that dense Monterey embankment down at that bottom layer of the embankment is saturated. And if you turn off flow and you have dense sands that are undrained, when you start to shear them, they will strongly dilate and generate negative pore pressures and develop really large strengths. And that strengthening in that zone was enough to kind of help suppress that rotational mechanism for the embankment. And so turning off flow was not conservative. Similarly, we said, well, what if we increase permeabilities? And so one way to do that is we'll set the permeability for that unsaturated embankment equal to the saturated embankment. So that means that Monterey sand is not only more pervious where it's saturated, but it's more pervious all the way through the embankment. We don't take into account any effects of partial saturation. In that case, it also reduced crest settlements by about 20 to 30% for these two events. And the reason is, with higher permeabilities in those two zones, you allow faster dissipation of pore pressures from the upper part of the Ottawa sand, which strengthens it and reduces deformations from these shaking events. And so turning flow off or increasing dissipation both reduce deformations, and we were kind of right in the sweet spot. Just an example of it's important to do these sensitivity studies because you don't really know which is going to be the more conservative set of assumptions. We also repeated the analyses going to the calibration of the cyclic strength for the model. As I mentioned, we used for the 0.26 G event, we had used a cyclic strength of 0.09. Well, what if it was the 0.12 that we had used for the 0.54 G event? We do that, that does reduce settlements by about a quarter to a third. And then for the larger event, instead of using the 0.12, if we'd reduced it and still used the 0.09, then you increase settlements by about a third. So that range of cyclic strengths would produce about a 30% swing in displacement. Now, another one we did was to just run the untreated case. So no soil cement wall, and if you do that, then you get displacements that are on the order of 3 meters at the crest, which is about 5 times what you measure with the soil cement walls. We didn't do a test without soil cement walls, but this type of model, we know from building other models and experiences, it would have really moved a lot for this level of shaking. And these numbers are kind of consistent with just showing that the soil cement walls really were effective at reducing deformation. So a couple points on discussion. I think the one item I wanted to kind of really emphasize is that we're testing these equivalent two-dimensional models. And it's for a pretty complicated system, and we are not modeling a whole bunch of different complicating mechanisms. So for example, if we think of those soil cement walls, we see in the experiment that you get extrusion of sand between the soil cement walls. That extrusion was greater near the downstream end where the berm could slump through the soil cement panels at the toe. And it was less up near the upstream side. But nonetheless, there's an extrusion mechanism that we're not modeling when you do 2D. Secondly, the walls develop these irregular cracking patterns. They develop offsets that vary along the length of the walls and between adjacent walls. So there's very complex cracking patterns. And we are using a more Coulomb model that does not model cracking. We get offsets with irregular, along those irregular cracks. When you get these offsets, you're going to get fluctuations of normal stress along those cracks. And we're below the water table, and the soils are saturated, and the walls are saturated. So you're going to get fluctuations in pore pressure everywhere that soil cement is cracking and in trying to offset. We know we have excess pore pressures in the sand between the walls. We measured that. And then when those soils have high excess pore pressures and the pore pressures in the soil cement shear zones themselves, they're likely to be negative. I say that because if you just look at some of the available lab test data on consolidated undrained testing of soil cement for this kind of loading condition, you will get these negative pore pressures. And for that reason, you would expect pore water to flow from the liquefied layers in between the walls, and it should flow into the cracks between the soil cement walls. And how fast that pore pressure can migrate is going to depend on hydraulic conductivities, crack apertures, wall thickness, hydraulic gradients, and all the other complicating factors. So that's pretty complicated. And that tells us that the shear resistance in those walls along those cracks is going to degrade progressively during shaking as the cracks offset and pore water moves around. We're not doing any of that. So we come to conclusions. The two-dimensional models gave pretty reasonable agreement with the responses from our centrifuge model. And that provides support for the use of these numerical modeling procedures in practice. And having said that, it's still important to recognize that there's limitations in what these models are actually recreating. So we see these soil cement walls. They had limited cracking in the 0.26 G event, but they sheared through in the half a G event. We see deformations in the treatment zone, complex cracking, offsets along the walls, extrusion of liquefied soil. So there's a lot of three-dimensional effects and nonlinear effects going on. The analyses used area-weighted properties of a non-degrading Moore Coulomb model with an average shear strength that applied throughout all of shaking. So there's quite a bit of approximation in there. Now, in practice, we recognize those limitations. We've been generally very conservative in how we pick those strengths and allow for the effects of tensile cracking and whatnot. But this seems to still work reasonably well despite all the approximations. So the analyses don't recreate those complex local behaviors, but it gets kind of the average resistance right. And in terms of what's important to us in getting overall deformations of the embankments, it seems to have worked reasonably well. The 2D analyses also showed that if you didn't have the treatment zone, we would have got much larger displacements. And that tells us that the soil cement walls are actually quite effective in reducing deformations, even though they're getting damaged throughout shaking in those stronger events. And that last punchline there is just that these soil cement wall grids have proven to be pretty effective as a strategy for remediating liquefaction effects in embankment dams, particularly where there's questions that other treatment methods may or may not work so well, depending on silty soil, sandy silts, and things where it might be hard to get densification effectively. So it's worked well, and these results kind of provide support for what we've been doing in the last decade or so in a number of these remediation projects. That brings me to pointing out in terms of the project, this was actually kind of a group of people interested in. I first should thank the National Science Foundation through both NICE and then NHERI for the support of the network and the support of the facility and all the capabilities that are available here for people to use. Experiments themselves were funded by the Pacific Earthquake Research Center. And this was during the year break between NICE and NHERI. And they were interested in supporting work that bridged issues in practice. And in that particular case, the California Department of Water Resources is an owner of one of these facilities and had been using these types of analyses, and they supported some of the numerical analyses that I was just describing. Also some help from Dr. Young Lung, Amber Polito, and all our centrifuge staff. And of course, we couldn't do anything if we didn't have the help of lots of people. That kind of gives an overview of this one particular project and how we helped kind of bridge an issue that was faced in practice. Being able to use the large centrifuge allowed us to build those kind of complex models with kind of that detail and be able to provide some validation for the practices that had been relied on already. I do want to just switch and see if I can do this right. Let's see, I'm going to do a new share and go. Oh, I can't find it. Let's go over here. Hopefully you're looking at our website. So if anyone's interested in some more details about the centrifuge model or the centrifuge facilities, you can go to our website for the Center for Geotechnical Modeling. Under the About Us menu, it gives a bit of the history, vision, there's descriptions of all our equipment. There are rate sheets, so if you're interested in knowing what it costs to do experiments, there's a equipment utilization form, that's some idea of what's involved in getting shared use. So I'd point you at this page if you're interested in details of the site. I'd also point you at, let's get to this other page here. Let's go here. We do a users training workshop at the facility, one a year. We've done, this is at the Design Safe website where you probably logged on to this webinar. And if you go to our facility under the workshop tab, these are the PowerPoints from our second users workshop and our first users workshop. And our third one is going to be Friday, May 18th. That is the target date. So if you're interested in that, you can always reach out to Design Safe for that. And then lastly, if you want to keep kind of informed about what's going on at the centrifuge, we have our Facebook page for the CGM. There's our illustrious former director, Bruce Cutter, and Dan Wilson, and former students. There's an ad for the REU program that is just filling in now. And you can join our website and follow it if you're interested in those. And so that's our unabashed marketing pitch. And then with that, I'll go back to the PowerPoint. And Mohammed, I don't know if you got any questions.
Yeah, there are some questions, but people also can unmute their computer and they can ask their question. But there are some of the questions that they could answer, and they were more about the centrifuge testing, but there are some questions that you might have a better answer. One of them was on the permeability. Like someone asked if what is the the permeability that you use. So the permeability that you use is at what level of relative density?
Yeah, so we, I don't know where I have that description, but Anna Maria did test for a range of relative densities. So we have in her thesis is a plot of hydraulic conductivity versus relative density. Between 42 and 45% relative density, it didn't change much. And so we just used this one value, corresponds to 45% relative density.
So the next one is about the shear modulus, if you measured it or estimated for the analysis.
A bit of both. So what happens is, let me see if I have that. We use Bender element arrays in some of our centrifuge models. And so doing Bender element tests just takes a certain cost and effort to put them in. We built a number of models with Ottawa sand where we've measured shear wave velocities. And so we know the range of velocities you're going to get for different relative densities. Those velocities are pretty consistent with small strain moduli that are in the literature for Ottawa sands. Alarson Guzman had a thesis which provided quite a bit of data. And then Anna Maria's thesis compiled data from them and others and provides the relationship for shear wave velocity versus relative density and confining strain. These numbers here, about 185 meters per second, are pretty reasonable numbers for what we're measuring in this sand. So it's a bit of both, a bit of the empirical lab database that matches up with our experience in measuring shear wave velocity in this sand.
So this The third question was on the parameter for PM4 sand. So someone asked if you have used the same parameter for PM4 model under the embankment and at the toe.
Yes, same everything.
And this is the last question. How do you think that your result could compare to those from real projects or case histories? It is quite clear that the result of both centrifuge and numerical analysis agree well, but it is unknown whether you are capturing the key aspects of the actual behavior of those dams or not.
Yeah, so the purpose of the centrifuge test and the analyses of them very much focused on the question of whether or not this 2D approximation with equivalent uniform more coolant model in the treatment zone will reasonably approximate the resistance we get in a set of soil cement walls as they crack and degrade during shaking. That's it. It's focused on that question. You can't really, if I'm understanding the question right, you can't really take this centrifuge model and compare it to any of those remediation projects in practice. Every one of those remediation projects in practice has a different set of loading conditions, ground motions, different kinds of sources, soil conditions are different, the geometries are different, everything is different. So we can't really draw from our conclusions anything other than this set of numerical modeling procedures and protocols worked okay for this centrifuge test. Now, that's better than nothing, because it gives us some sense that the approximations were at least not badly off. We then use those same protocols in the application to the real projects. And in those real projects, they always involve a sensitivity study to make sure that the decisions being made are not sensitive to estimates of the shear strength in the soil cement, cyclic strengths in any liquefiable layers, strengths in the non-liquefied embankment, or ground motions. Pretty cautious in making sure the design is robust. It's never going to be designed right on the edge of any one set of things.
Would you please mute your computer when you are typing or doing something noisy? So there is one common question that I got a lot is about boundary condition. The question is how you consider those boundary conditions and how it's going to affect the results.
Right. So common problem in centrifuge modeling is that you cannot avoid boundary conditions. Now, in reality, you can't avoid boundary conditions either. Everything we do has a boundary. The question is, are we representing the boundaries reasonably? To the degree that what we're really testing is whether a numerical model can recreate the behavior, it should not be sensitive to, when you look at this particular problem, if you want to simulate this behavior, we have learned that you have to model the container. You do a rigid container, it's a rigid boundary. Equivalent shear beam, we model the equivalent shear beam. We do hinge plate, we model those boundary conditions. But you have to include the mass and stiffness of the boundaries, or it's going to change the dynamic response of the system. Have to include them. Second thing, though, is it's about as predictable a thing as we do. We predict elastic response quite well. We know the properties of the aluminum, the mass, the stiffness of everything. That is a very predictable response. And so the model still comes down to how well can you model the nonlinearity and other features of behavior of the soils and the structure systems inside the container. So I'm not sure I've got the kind of focus of the question or understood it correctly. The answer is no, you cannot get away from boundary conditions. You have to embrace them. You have to actually include them in the numerical simulation. You can't ignore them.
Yeah, and I think the last question is about the references where they can find the papers and publications on this project.
Yep. So what I'm going to do is I'll bounce all the way to the end here. And at the end of this PowerPoint, I actually have a couple pages of references. But I'll point you at this one in particular. And the one you can get is we have a paper that was published as part of the performance-based design in geotechnical earthquake engineering up in Vancouver in July. We have a version of that which will appear in the Soil Dynamics and Earthquake Engineering Journal, but it won't come out for a little while. And then both of those papers will contain all the references that are contained on these two slides. This particular one, they're supposed to be posted at the library for the International Society of Soil Mechanics and Geotechnical Engineering. But if anybody wants a copy and you can't find it, all you have to do is email Mohammad or me, and we will provide you a link. Now that said, let me, I'm not sure if I have that. 1 second. There we go. I also post all my papers on my homepage at UC Davis. And if you go on the publications tab, there is a link. So there's all the papers. PDFs are not there because you're not supposed to post them openly, but there is a link there that says only for friends. And the password is friends. So if anyone's interested in seeing any of these papers, I'll make sure that that one is posted there. If not already. Homepage, publication tab, only for friends. You'll ask for a password, it's friends.
So another question, did you find the results sensitive to stiffness of the shear panels?
No, it's a good question. In general, we were using 600 times the shear strength or 300 times the unconfined compressive strength. That's a pretty common number. I think you'll see that in the FHWA manual. It's like a secant value allowing for, it's not the small strain stiffness of the soil cement, but it's kind of like a secant value at some higher strain level. And generally the soil cement is stiff enough that within about a factor of 2 up or down, it made very little effect on deformations. We didn't go any further than plus or minus a factor of 2. But in that range, it wasn't sensitive to.
So another question about the boundary condition. It says, what effect, if any, do the edges of the container contribute to the results in this testing?
Yeah. Make sure if I understand the thrust of that question, I'll elaborate on one other thing. This is a 2-dimensional model. And in the 2-dimensional model, and I said you have to embrace and model the container. In modeling the container, what we're doing is taking the mass of all the rings, which are 3-dimensional, and the stiffness, which is 3-dimensional, and then proportioning them onto the equivalent out-of-plane thickness of the soil so that you get the right relative stiffness of the soil and the overall container, right? So this thing is about, let's say models about 40-meter wide soil column, and then you have stiffness of 40 meters of soil, and then the container, and then they're weighted, so you get the relative stiffness right.
Yeah, but the question is about the centrifuge model. So those edges, those corners, are they going to affect the displacement of the embankment?
Yeah. So when you say corner, so I thought the question was going to be in the true centrifuge model, it's 3-dimensional. And so you have some side shear all the way along the sides where the container is up against the side walls of the container. Generally, we evaluate that by looking at, in plan view, when you dissect, you look at whether or not deformations are going uniformly across the model or whether or not you get some bowing. And generally, we get very little bowing, so that suggests the side friction is not a dominant factor in any way or major factor in any way. you definitely have the influence of the container. So the soils here can't move away from the container, and here they're blocked by the container. So the deformations will be restrained by the bottom container. Deformations here are restrained. When you look at this kind of behavior, you see the upper wedge of the embankment is actually sliding backward. The reason is when you shake this and this soil liquefies, there is more earth pressure against this wall of the container than there is against the right side. What that means is the container will actually deform left. This container wall is tied to this wall, so the container actually racks slightly to the left. Then you get this graben forming against the container wall, and then this block here moves towards the right, shears through the walls, moves over here, and then you get some piling up of material up against the bottom wall. Absolutely, the container boundary affects the response. Question is whether the numerical simulation recreates that response.
So I think there is no more question. Do you have anything else, Ross?
No, other than I'd say thank you to everyone for joining in. Keep your eye on the other NCO Design Safe webinars that are coming up. As I said, if you go to our website or our Facebook page or the Design Safe website, you can follow what's going on at the facility or learn more about the other projects. And we're always looking for new users. So I hope everyone got something out of the talk. And if you have any questions, just let us know.
Yeah, if you have any question, you can also email me and I can send you information about the test and other stuff. And I will put my email here in the chat list.
Great. Thanks, everyone.
Thanks, everyone.
Thank you, Ross, and thank you, Mohammed.